Okay. Hello, everyone. Thank you for joining DataCon LA 2021. Welcome to the data engineering track. My name is Eli, your host, and our co-host today is Lori. We will be moderating the chat and Q&A for you during the session. Today, we have our guest, Vitaly Polonetsky, who will be discussing Spark challenges. Vitaly is a tech leader, mentor, and big data architect. He has 7 years of big data experience with Apache Spark and Hadoop, and more than 20 years of software development experience. Without further ado, I'll hand this over to the speaker. Thank you for being here, Vital.
Hi, thank you, Lori and Eli. Let me start my share here. Okay. So my name is Vitaly Polonetsky. I'm a senior staff software engineer at ZipRecruiter. Few things about ZipRecruiter. ZipRecruiter's mission is to actively connect people to their next great opportunity. And ZipRecruiter acts as a marketplace between available jobs and job seekers, where all sides benefit from high quality data and matching models. As we collected more and more data at ZipRecruiter, we started investing into Apache Spark as one of our main big data processing technologies. My personal big data processing experience started with Apache Hadoop MapReduce jobs almost 9 years ago. And in 2016, I started migrating data pipelines to the new and shiny Apache Spark. Over the years, I mentored software engineers to focus on data engineering. And in this presentation, I've created a compilation of challenges of mine and others when processing data with Apache Spark. So the topics I'll cover in this talk are the typical timeline and milestones of data processing projects, the different origins of data skew issues and their effect on the processing pipeline. I'll talk about optimizing Spark dataset joins. I'll also talk about other types of optimizations we can do to reduce wasted processing time. I'd like to do some quick recap of Spark memory configuration. And finally, we'll have some time for a Q&A session. So let's start with typical data processing project stages. The first stage will be start by collecting the requirements. We usually look at the inputs and the outcomes we want to get out of the data processing project. And the outcomes can be, for example, provide a new KPI of how we want to measure our business, or maybe we want to prepare a data set for a machine learning algorithm to improve our product. Then we go into coding and deploying cycles to test that our code works well. And finally, we deploy to production, set up monitoring according to the SLO we aimed for, and start celebrating. And now let's see what happens at this last stage when we're celebrating. We deploy to production and everything works well. And let's assume that we have a stable set of requirements here, so we don't have to go back to the first stage of re-implementing because something changed in our requirements. But data will change over time, usually when the business is doing great. Maybe we started a new marketing campaign that attracts new users. Maybe some other part of the business released a new product feature that started generating new types of data. And finally, maybe the popularity of the product drives more fake traffic like bots. These changes in the shape of the input data can cause the pipeline to fail. When SLA is breached, we tend to find the quick fix because business is waiting for the outcomes of our data pipeline. One of the easiest things to do is to increase the memory usage of our Spark jobs. For example, if it failed for out-of-memory error, increasing the memory sounds like the first candidate. We do it once, we do it second time. Now we remember that it works as a quick workaround to fix the issue, and we keep doing that. But eventually, the data changes in its shape so much that increasing the memory limits won't help as much or won't help at all. And now we have to go back and fix the code or completely rethink the way we process this data. In addition to that, if we start looking at wasted resources, more often than not, we'll find that these types of quick memory limit increases caused us to waste resources. Maybe a few of the Spark executors actually benefited from that memory increase, while the rest were sitting idle after they processed their assigned tasks. If we designed our pipeline to scale linearly with data increases, we could just increase the number of Spark executors. But with almost any real-world data processing pipeline, we would need to perform deduplications or joins that are causing shuffle of the data between partitions, and the runtime increases become nonlinear. If we go to the stages diagram, we can see that the problem originates at the collect requirement stage, where we perform data exploration. At that step, we can only look at the state of the data at that point in time. If we put more effort at that stage, we'll be able to predict some of the ways how the data might change over time or grow, and we'll be fine as long as the input data will stay within those boundaries that we thought about. Let's talk about data skew, which is one of the ways the input data might change that will cause these type of issues and failures. On this slide, the circles represent data records with some property. In this example, we have a property of a color that the circles are different. And they're distributed into 4 different partitions in 2 different ways. In the example on the left, we didn't partition the data based on color. Maybe we partitioned the data randomly, or maybe based on some other property. In the example on the right, the data is partitioned by the color property, and as you can see, the color distribution is skewed. Partition 1 has much more data than the other partitions. If we were to count the number of records, the task that calculates the count for the first partition will have to read more data than the other tasks, and therefore will take more time and resources. Eventually, what we see on either of the sides can be how the input data is stored within the storage layer, and processing it in Spark might shuffle it to look the other way around. So for example, we can start with the data that looks more like what we have on the left side, where the data is well distributed, and as part of our Spark processing pipeline, we need to reshuffle the data, and it would start looking more like what we have on the right side, and vice versa. One example of this skewed distribution could be with the storage of job seekers. Maybe we partition job seekers by the year they register for the service. And in a specific year, we have a very rapid growth of job seekers. So that year's partition in our storage layer will have much more records than the other years. When input data is skewed, we might need to go upstream to the process that created our input data and either repartition the data before it gets written, or make sure we use optimal storage format and compression that allows splitting a single storage partition to multiple Spark dataset partitions to reduce the effect of the data skew. The input data might be fine, but then as part of the data processing, we might be introducing data skew. Usually when we need to group by or join based on the skewed property of the records. Here I created some examples of the symptoms of the data skew. We can look at the Spark UI to see the early symptoms of it. The first example is the timeline that you can see at the top. One task is taking roughly the same amount of time as 9 other tasks. And in the second example, we have the task list. It's sorted by the duration of each task. And you can see that the top tasks are taking much more time than the other tasks. And you can also see in the same problem in the statistics at the third example, where the 75th percentile looks much closer to the median values than the max values. With these symptoms, our pipeline might become slightly slower. And finally, if we miss the symptoms, we will start seeing out-of-memory errors and lost executor exceptions, where an executor is killed by the resource manager or stuck in garbage collection for too long, such that it can't send a heartbeat that it's alive. Like I mentioned, most of the time Spark UI or Spark History Server is useful. It shows shuffle sizes per partition or total number of records across all partitions. In some cases, you won't be able to use the Spark UI, either because it doesn't provide the right level of detail, or our job is failing and preventing the population of the UI is shutting down and the Spark history server is not populated with the latest data. We can use these simple queries to read the data at any point in time in our data processing pipeline. But where would we run these queries? I wouldn't run this as part of the production job to monitor the distribution at every stage. I'd use the existing metrics that are coming from the job to monitor a working pipeline. If the job is stuck, we can use a combination of Spark UI and these queries to pinpoint the issue. Maybe control these with a feature flag that you will be using during incidents only. There are other ways to explore the data. For example, we use AWS Athena to look at the shape of the data, and there's a very useful virtual column called $path that you can use to see where the data is actually stored on the storage layer. But there are other ways to improve our data processing pipeline. This is how we monitor and test our Spark jobs. We invest a lot in data exploration and development experience solutions. The first one I want to talk about is the ad hoc data exploration tools like Jupyter Notebooks and AWS Athena. I mentioned that we use this to query for ad hoc analysis and explore the data at every stage of the project. Then we also have the performance test deployment here, where we can test our pipelines with high volume of data. We also have centralized real-time monitoring and logging systems where we can monitor current data shapes and amount of CPU and memory usage. And finally, our auto-scaling cloud-based infrastructure is really helpful. It allows us to run multiple tests at the same time with different parameters and look at the resources we're using and tune these resources on the fly. All these allow us to get alerted on issues, find the root cause of the problem, test, and release a fix with minimal effort. Most of the time, these unexpected and hard-to-fix failures will be related to a data skew in a join. So let's talk about dataset joins in Spark and the ways to optimize them. When talking about dataset joins in Spark, there are 4 important properties of the join that we should be discussing. The first one is the data volumes. We want to understand whether one side of the join can fully fit into memory of a single Spark executor. The second property would be what are the joined columns we have, whether they're sortable or whether they're part of the existing partitioning of one of the sides. One quick note here. When we need to join large data sets, I would prefer to use columns from existing partitions of the joined data sets to reduce the shuffling of the data. For example, if 2 sides of the join are already partitioned by dates, I would be using date in the join condition in addition to exact timestamps if I need to join by the exact timestamps. The third property of the joins is the operator we're using. There's a big difference between an equijoin or non-equijoin operator. When we use equals operator, it's obviously an equijoin, and it has different properties than non-equijoin. And finally, we have different join types like inner, cross join, left, right, full, outer joins, and others. And based on these properties, Spark will decide on the join strategy it will be using. On this slide, I created a compilation of features and requirements of each of the join strategies in Spark. It's well documented, and you can use the link below to read the text version of this table. You can use hints and change Spark's config to ask Spark to choose a specific join strategy if multiple strategies meet the requirements. Here, I've ordered the join strategies from left to right based on the order in which Spark will prefer to execute them for equijoins. As you can see, the leftmost join strategy will have more limitations, but will also be more performant. As you keep adding requirements, Spark will be preferring the other join strategies, and one example of pushing the limits of Spark joins would be with a full outer join with a between condition. Spark would have to choose the broadcast nested loop join shown on the right column and will be highly dependent on the size of the data, as you can see from the memory requirements row here. Basically, every type of join that would cause us to find non-matching rows would be much more harder on Spark than doing an inner join. There's an interesting feature that was added in Spark 3.0 that is called Adaptive Query Execution, or AQE for short. It has to be enabled explicitly in the Spark configuration. It's not the default, but it can help in 3 ways, and all of them are relevant for joins. So the first one is Spark will be coalescing post-shuffle partitions. Joins will cause a shuffle, and if after the shuffle we have a lot of partitions with a low amount of data, Spark will be able to coalesce those into bigger partitions. The second feature is converting sort merge join to broadcast join. When Spark runs the plan, and based on the statistics as part of the run, it will be able to detect that some of the data sets are small enough to fit into the broadcast join requirements, and will be able to convert sort merge join to a broadcast join. And finally, Spark will be able to optimize skew join, where we have one partition that is highly skewed. We'll be able to optimize it and split it into smaller partitions. But even talking about that, maybe we can avoid the skewed dataset joins completely. I first try to separate the concerns. Deal with the skew first, separately from the join. And in most cases, this data skew is also a pain for the business. Maybe we have a group of fake users, like bots, that generate significantly more traffic than real users. Maybe we have data property that is so common to all user activity that it doesn't make sense to include it in our join. For example, maybe we have a too common of a job seeker skill. It might be easier to convince the business to drop the outliers early in data processing, or split those to a separate, less demanding data pipeline. I also want to mention other Spark optimizations that are useful not only with joins. Let's not forget that each Spark action, like count or write or collect, is very expensive. Developers think about the following ideas as helpful, but they will slow down the Spark data processing pipeline, and in most cases for no good reason. So the first one about maybe putting a conditional and checking whether the data set or data frame is empty or not. It's a feature that is built in into Spark. If you perform some action and the data set is empty, that action will have no effect or no special effect, right? The second one is about calculating the aggregates, like count, min, and max of some column. It also forces us to use persist or checkpoint because we don't want to reprocess the data fully multiple times. For the most part, the same can be achieved with accumulators. You can see them in Spark UI, you can log them at the end of the job, or you can monitor their value in the middle of the job run using Spark Listener. With the last one, where we break down a single input into multiple Spark jobs, we're effectively taking control of the data partitioning into our own hands. It requires writing our own progress persistence, which is error prone, and in most cases not needed, as Spark can do a great job with partitioning data. Also, I hear a common suggestion to repartition datasets into the multiply between number of executors and number of cores. That will give us the best parallelism. Every single partition will be processing data at the same time from the beginning. But with long-running tasks, we will lose visibility and fault tolerance aspects of our job. Imagine on average it takes 1 hour to finish a single task. If we go with this recommendation, a single task that was close to completion but failed because of intermittent failure will retry, adding another hour to our job processing. A better approach is to set the number of partitions by timing the tasks, and I like to aim for 1 to 2 minutes of execution time to see the tasks progress. So I would try to set number of partitions as high as I can to still meet this requirement or this suggestion of 1 to 2 minutes per task. Combining the two suggestions is probably a good idea too. We will be able to use a multiplier in addition to number of executors time number of cores.
I
Side
just
note,
wanted to let you know about 10 minutes before Q&A.
oh, thank you. Side note, this suggestion is not applicable for the barrier execution mode that is required by some deep learning algorithms. And eventually, we might still need to increase the memory. Maybe a single row is growing in size so much that we won't be able to not increase the memory and optimize jobs in a different way. So I wanted to do a quick recap of how Spark uses memory, or what are the different parts of the memory usage. As you can see, the executor side of Spark will be using usually a resource manager, unless you're using the local resource manager that runs everything within a single JVM. So outside of that, the executor will be running within a resource manager. You can set the requirements on the JVM heap side. You can also add additional memory requirements as your off heap or other processes that are running within that container. And the same also goes with the driver of Spark when we're running in cluster mode. A common confusion I see is with the client deployment mode. In this mode, the JVM process will start inside the current container, so you can't control the resource manager configuration for the driver using Spark configuration parameters. And you also can't control the driver's JVM heap memory if the JVM process has already started. I think I reached the Q&A a bit earlier, but I also wanted to point out that I'll be hosting some of the examples that I used to prepare this presentation on my GitHub. You can see it here, the link to it. And I wanted to say that at the end of the day, processing data with Apache Spark can be challenging at times. But if you invest time in understanding the shapes of the data and monitor its trend, you can build reliable and efficient data pipelines.
Thank you, Vitaly. Let's open it up for questions. If you have any questions, please put them in the Q&A section. I have a question about how large are the large skews that you would see in data from something like a job trait that is overwhelmingly popular.
I won't go into that specifically, but for example, one of the skews that can happen is if one of the properties is null and we still want to join based on that property. That's, I would say, the highest skews that I see, where, for example, there's like multiple features on our website, for example, and some job seekers are not falling in one of these features, and we still want to join them with some other data set.
So you guys use AWS, is that right, for
Yep.
scaling out your services? Uh, is it so? I noticed that you said alternative sort of ways to run it on Kubernetes and things. Are you guys running it on Kubernetes on AWS, or
Yeah,
is it?
we are deploying our data pipelines on Spark that is running on Kubernetes on AWS. Yep.
Okay.
We have to invest a lot. It's an interesting way to run it, but the benefits are it's just incredible how fast we can spin up new pods and
Right.
get new clusters running.
Yeah. I'm always impressed that Kubernetes is additionally managed Kubernetes stuff. It's really
Yep.
nice to.
I have two more slides that I
Oh,
uh,
yeah, yeah. Go ahead.
was
Share.
thinking about including as well, if there are not much
Yeah,
questions.
yeah. No questions yet. So
I, I wanted to talk about how Spark API is confusing sometimes. And in this case, this is probably um, uh, my first interaction with Spark when we used to write MapReduce jobs. And I saw that based on the benchmarks, Spark is faster, right? So I took one of the MapReduce jobs and I was trying to convert it to use Spark, and I saw that there's a group by key API that looks very familiar to the reduce API of Hadoop. And when I tried to use it, obviously, as you can imagine, it threw an out of memory error. And the problem that I discovered like back then is that the iterable that you see here is confusing, because the iterable on the Hadoop side would usually be backed by storage. So you can iterate on something where not all of the values of iterable fit into memory. Whereas here, iterable, where it's part of the RDD type definition, it would have to be stored in memory. Now, this is slightly different from a different API that Spark has that is called map partitions that I really like. So map partitions doesn't produce RDD that has some type that includes iterable. So you will be able to get iterable as part of your function invocation, and that iterable is backed by disk. And another thing that I find people struggling with is the terminology around the Spark clusters. So, for example, Spark job has two parts to it. There's the driver job, the driver part, and the executors part. So, as you probably know, driver is where our code is running. Like when I'm doing .map or .save, the .map is running on the driver. But what the driver will do is it will communicate the plan, what we want to do, to the executors, and executors will execute the function that was passed to the map. Or in the dataset world, it would communicate with the executors and tell them what to do, right? Not specifically a function I wrote. The second type of confusion is with the resource manager, where we have the master and worker nodes. So this is purely a resource manager terminology. Spark driver can talk to the resource manager master to ask for more executors that will be running on the worker nodes. And finally, with Spark submit, cluster and client deploy modes are also confusing. I like even their names are confusing when I'm thinking about those names. Cluster means that we have a separate cluster that we want to run our job at. So our where we execute the job can talk to a cluster. And in client deploy modes, it means that we're already part of the cluster and our job is running within that cluster. Our driver is starting within that cluster. That's just a few additional slides I had.
It's very interesting. I hardly do any work on Spark, only for testing purposes, and it's a lot of knowledge you have to possess in order to make it work correctly.
It gets easier.
I hope so. All right. So thank you, Vitaly, for your presentation and the attendees. You can contact the speaker directly if there are any further questions regarding this topic. Please provide your feedback using the form provided in the chat box. Thank you again, everyone, for joining today's presentation. I hope you have gained some insights from this session. Have a wonderful day. And thank you for being a part of this year's DataCon. Thank you again.
Thank you. Bye-bye.
Thank you.